Hello science fans, today we are going to explore something truly electrifying. We are diving into the world of RLC circuits. Now that might sound like a secret code, but I promise it is not. It is actually very simple when you break it down. An RLC circuit is a fundamental building block of electronics. It is made of three special parts. We call them a resistor, an inductor, a capacitor. These three components work together in a circuit. They control the flow of electricity in fascinating ways. Think of them as a team, each with a unique job to do. So why should you care about these circuits? Because they are everywhere. They are hidden inside so many of the devices you use every single day. Your radio, your television, your phone, they all rely on the principles of RLC circuits to work their magic. Understanding them is like getting a backstage pass to the world of technology. It helps you see how simple components can create complex and wonderful things. We are going to take a journey step by step to understand each part and how they cooperate. First up on our team is the resistor. Its name gives you a big clue. It resists. A resistor's main job is to control the flow of electric current. Think of electricity through a wire like water in a hose. Squeeze the hose and less water gets through. A resistor does the same for electricity. It squeezes the path for electrons, making them harder to flow. That reduces current through that part of the circuit. It's like a traffic controller for electrons. Resistors protect delicate components. Too much electricity can damage parts. The resistor steps in. Whoa, slow down! By limiting current, everything runs safely. We measure resistance in ohms. Higher ohms equal more resistance. Like making the hose narrower and narrower. You can spot them on a circuit board. Tiny cylinders with colorful stripes. Those stripes aren't decoration. They are a color code. The code tells you the resistor's value in ohms. It converts some electrical energy into heat. That's why devices get warm. Next, let's meet the inductor. The inductor, represented by the letter L, is a fascinating component. It is usually just a coil of wire, sometimes wrapped around a core made of iron, or another magnetic material. Its superpower is related to magnetism. When electric current flows through this coil, it creates a magnetic field around it. The inductor stores energy in this magnetic field. Think of it like winding up a toy car. You are storing energy in the spring. The inductor stores energy in its magnetic field. It is a bit like an energy savings account for the circuit. The inductor has a very particular personality. It does not like change. Specifically, it resists changes in the flow of current. If the current tries to increase suddenly, the inductor pushes back, trying to keep it steady. If the current tries to decrease, the inductor releases its stored magnetic energy to try and keep the current flowing. It is like a stubborn mule that wants to keep moving at the same speed. This property is called inductance, and we measure it in henries. Imagine you are pushing a very heavy flywheel. It takes a lot of effort to get it spinning, right? It resists your initial push. But once it is spinning, it wants to keep spinning. It has momentum. If you try to stop it suddenly, it will push back against you. An inductor smooths out the flow of current, preventing sudden spikes and sudden drops, which can be very useful in many circuits. This opposition to change is the inductor's defining characteristic. It acts as a buffer, ensuring the electrical current remains stable and predictable. Now for the final member of our trio, the capacitor, represented by the letter C, another energy storing device. But it works differently from the inductor. Stores energy in an electric field, not a magnetic one. Think of it as a tiny, very fast rechargeable battery, made of two metal plates separated by a dielectric. Connect to power, positive charge builds on one plate, negative charge builds on the other plate. It charges up and holds that energy. It can hold charge even after disconnecting the source. Provide a path and it discharges very quickly. Releases stored energy in a sudden burst. Think of it like a water tank. Slowly fill the tank. Charging. Open a large valve. Water rushes out. Discharging. The capacitor also has a unique relationship with electric current. Blocks steady direct current. Once charged, no more DC flows. The insulator between the plates creates a gap in the circuit, but it allows alternating current through. AC constantly changes direction. Capacitor continuously charges and discharges first one way, then the other. From AC's view, it looks like current flows through the capacitor. Electrons aren't crossing the gap. Role in RLC, energy reservoir. Stores electrical energy in an electric field. Blocks DC but allows AC. Separates signals, measured by capacitance in farads. Uses smoothing power supplies. Uses camera flash. Delivers a quick jolt when needed. The sprinter of the team, ready for a burst. Now that we have met our three amazing components, let's see what happens when they work together on the same team. An RLC circuit is simply a circuit that contains a resistor, an inductor, and a capacitor. They can be connected in a couple of different ways. The most common are series and parallel. In a series circuit, the components are connected one after another in a single loop, kind of like beads on a string. The same electric current has to flow through each one. In a parallel circuit, the components are connected across the same 2 points, offering different paths for the current to take. When you connect these 3 components to a power source, especially an AC source where the voltage is constantly changing, a fascinating dance begins. This power source provides a voltage that wiggles back and forth very quickly, like a sine wave. The resistor is always there, resisting the flow of current and turning electrical energy into heat. It tries to keep the current and voltage in step with each other. The inductor, resisting changes in current, causes the current to lag behind the voltage. It's almost like the current is playing catch-up. The capacitor, which must charge up before the voltage across it is at its maximum, causes the current to lead the voltage. The current sort of gets a head start. So, in an AC circuit, you have this push and pull effect. The inductor wants to make the current late, and the capacitor wants to make it early. They are essentially working against each other. The resistor is just there, doing its job of limiting the overall flow. The total opposition to the current in an AC circuit is called impedance. It's a combination of the resistance from the resistor and the opposition from the inductor and the capacitor, which we call reactance. The inductor's reactance and the capacitor's reactance have opposite effects on the timing of the current. This interaction is the heart of what makes RLC circuits so special and so useful. The energy in the circuit sloshes back and forth between the capacitor's electric field and the inductor's magnetic field. The resistor gradually drains this energy away, converting it to heat. Think of it like a pendulum swinging back and forth. The capacitor is like the pendulum at its highest point, full of potential energy. The inductor is like the pendulum at its fastest point in the middle of its swing, full of kinetic energy. The resistor is like the air friction that slowly causes the pendulum to stop swinging. Now we get to the most exciting part of our RLC circuit story, resonance. Resonance is a special condition that happens at one specific frequency. Remember how the inductor and the capacitor have opposite effects on the timing of the current? The inductor makes it lag, the capacitor makes it lead. There is a sweet spot frequency where these two effects are perfectly equal and opposite. At that frequency, the inductor's lag cancels the capacitor's lead. It's like two equally matched tug-of-war teams pulling on a rope. The rope does not move. When that cancellation happens, only the resistor is left to oppose the current. The reactances of L and C effectively vanish. So the circuit's total impedance is at its absolute minimum at resonance. What happens then? Maximum current flows through the circuit. The circuit passes that one frequency very efficiently, while it strongly resists other frequencies, both higher and lower. Think of it like pushing someone on a swing. Push at the swing's natural rhythm, the resonant frequency. Small pushes add up and the person goes higher and higher. Push at the wrong rhythm, too fast or too slow, and you fight the swing. It won't go high. An RLC circuit is just like that. With an AC source at resonance, the current can reach very large amplitude. Energy sloshes back and forth perfectly between the inductor and capacitor. Resonant frequency isn't random, it's set by the values of the inductor and the capacitor. Choose L and C and you tune the circuit to your desired frequency. You can calculate it precisely. This ability to pick one frequency and reject others is hugely useful. It's the principle behind tuning a radio, filtering signals, and many other electronics and communications applications. So we know that an RLC circuit can be tuned to a specific resonant frequency, but why is that so important? The answer is selectivity. Imagine you are in a crowded room where hundreds of people are all talking at once. It's just a wall of noise. But you want to listen to just one person's voice. If you could somehow amplify that one person's voice and tune out all the others, you could have a clear conversation. This is exactly what a resonant RLC circuit does for electronic signals. Think about your car radio. When you are driving, the radio's antenna is being hit by signals from dozens of different radio stations all at the same time. There are stations at 92.5 MHz, 98.7 MHz, 101.1 MHz, and so on. All these signals are creating tiny electrical currents in your antenna. The radio's job is to pick just one of them, the one you want to listen to, and ignore all the rest. How does it do that? It uses a tunable RLC circuit. When you turn the dial or press a button to change the station, you are actually changing the value of the capacitor or inductor in the radio's tuning circuit. By changing the capacitance or inductance, you change the resonant frequency of the circuit. You are adjusting that sweet spot we talked about. When the circuit's resonant frequency matches the frequency of your favorite station, say 98.7 MHz, the circuit allows the signal from that station to pass through with maximum strength. At the same time, it presents a very high opposition to all the other stations' frequencies like 92.5 MHz and 101.1 MHz, effectively blocking them out. This is how you can hear one station clearly without interference from all the others. This principle of filtering is not just for radios. In audio equipment, RLC circuits are used in equalizers to boost or cut specific frequencies like the bass or treble. In power supplies, they are used to filter out unwanted AC ripple to create a smooth DC output. In wireless communication, they are used in both transmitters and receivers to make sure devices are talking on the correct channel. The ability to select, filter and amplify specific frequencies using resonance is a cornerstone of modern electronics. Without it, our world of communication would be a chaotic mess of noise. We have been on quite a journey, from meeting the individual components to seeing them work together, discovering the magic of resonance. Now let's bring it all home. You might be surprised. RLC circuits are everywhere, not just labs, inside devices you use every day. Radio, resonant circuits pick the right frequency. Television, tuning and selecting channels. Wireless devices, routers and radios pick frequencies from a sea of signals. RLC circuits also power signal processing. They can be designed as filters. A low-pass filter lets low frequencies through. It sends deep bass to a big subwoofer. A high-pass filter does the opposite. It lets high frequencies pass. Ideal for sending sharp, crisp sounds to a tweeter. These filters make sure the right sounds go to the right speakers. Another key application is in oscillators. An oscillator creates a signal of a specific frequency. RLC circuits are often at the heart of these oscillators. Energy sloshes back and forth at resonance to generate a stable waveform. These oscillator circuits are the heartbeat of many digital devices, computers, smartphones. They create the clock signal that synchronizes all microprocessor operations. Without a stable clock oscillator, your computer would not function. From the moment you turn on your Wi-Fi router in the morning to listening to music on your phone to watching TV at night, you are interacting with technology powered by RLC circuits. They are in power supplies, communication systems, audio equipment. They are the fundamental building blocks that let us control and manipulate electricity precisely. Resistor, inductor, capacitor. Together at Resonance, you've unlocked a key secret behind modern technology. Science is everywhere, even in the simplest of circuits.